Welcome to the lair of the Batty Boffin.
Hi there Batty fans, a little bit more about electricity, and here we're not going to be doing any calculations with little circuits and lights and batteries. We're talking more about the kind of electricity that you use in everyday life, and this is the kind of stuff that comes out of the sockets in your walls. Now, fabulous drawing here, took me a long time, I hope you like it. We're talking here about direct and alternating current and the national grid. Now in Britain we have a thing called the national grid. Most other countries have something similar, and this means that you have lots of places that generate the electricity, and then it's distributed all over the country to all the places that need it. What this means is that if Birmingham needs some power, you don't have to actually generate it in Birmingham. Occasionally people don't use the national grid. If you're in very rural areas you might generate your own power locally, but most countries have a national grid of some form. So, first thing I'm going to do is just talk you through my fabulous diagram over here. On the left here we have ways of generating electricity. Now there are loads of ways of generating electricity, but basically they all boil down to the same thing. It's involved in turning something like this, which is called a generator. Sometimes we use wind turbines. I happen to live about a quarter of a mile from a wind farm and I love it. And those obviously turn themselves by the wind, so you've got the turning thing going on in here. All the other ones, the coal-fired power stations, the gas-fired power stations, the nuclear power stations, all of these do something to generate heat. That heat heats water to cause steam, and that steam gets put into the generator to turn it, and so you've got your turning motion again. Hydroelectrics work exactly the same way. It's like the old water mills. Again, you're turning something. So they basically all end up turning a generator. Now there are other Batty Boffin videos. Look in the electromagnetism series to find out things like motors and generators and all that kind of stuff. But a generator is basically an electric motor backwards. If you have an electric motor, you put electricity in and it turns something, like a wheel for example. A generator is exactly the same thing but backwards. You do the turning and you get electricity out. Very clever. So here's my generator turning round and it's generating electricity. Now, most power stations in Britain anyway generate electricity at somewhere round about the 25,000 volts, which is a lot of volts. But strangely, even though they're generated at such high voltage, the next thing you do is you transform it. You use the transformers. That's not transformers, robots in disguise, not that kind of transformers. It's a transformer that changes electricity, and it changes it from high volts to even higher volts, from which it gets put onto these we have pylons in Britain, other countries will bury them under the ground, and these come at around 400,000 volts. That's nearly 500,000 volts, which is a really, really high voltage, and we're going to talk about in a minute about why it is such high voltage. So we've got it coming out of your power station through a transformer, and again if you look in the electromagnetism series it'll tell you all about transformers and how these coils work and everything like that. But just take in mind that here it's the same kind of thing as you may have at home, but usually those will be step down transformers, things like fairy lights or scale electric cars and things. They have transformers to take your household electricity, which is at say 230 or 110 volts, and to transform it down into something like 12 volts. Here we're transforming it up from 25,000 to 400,000 volts. It then gets carried along the country on overhead or underground wires until it comes to another transformer down here, and in fact there could be several transformers. Sometimes in Britain we have these kind of boxes every now and then on the side of the roads, and those have often got transformers inside them. So that will step it down to, in Britain, 230 or we often use 240 for calculations because it's easier, but it's actually more like 230 volts. In America that's 110 volts, and that's for your domestic use. So you're probably asking me, why don't we just generate it at 230 volts? Well, we'll be talking about that in a minute. But there's something else we need to know about this electricity as well. It's not the same stuff that you use in batteries. We have two types of electricity. One is called direct current and one is called alternating current, and transformers only work with alternating current. What's alternating current, I hear you ask? That wasn't very loud. Well, I'll tell you. Direct current is the stuff we get from batteries, and if we plot a graph of time against voltage, we find that the time and the voltage just makes a straight line like that. If it's a 9-volt battery, those little rectangular ones, then it'll give out 9 volts. And every time you measure it, it's 9 volts. Alternating current, on the other hand, does something more like this. It flips from positive to negative, to positive to negative, all over the time. And in Britain, it does this at 50 times a second. And the unit for times a second is this HZ. It's not Heinz, not beans, it's hertz. And that's not car rentals either. 50 hertz is 50 times per second. So in Britain, if the electricity that you get out your sockets alternates from positive to negative and back again 50 times each second. That's a bit peculiar, but again, when we look at motors and generators, you'll see why that happens, and it is necessary for transformers to work. Transformers won't work on direct current. They only work on alternating current, or AC, which is why we use AC, the stuff that comes out of your plugs. So these things here are going to generate 25,000 volts AC, and this is all AC, alternating current, coming all the way to your house. Okay, so I'm going to wipe down this board, get rid of my beautiful drawing, and we're going to talk about why it's 400,000 volts in the pylons. I'll see you in a minute. So, why do we put things up to such great big high voltages to transport it, only to step it down again at the end with a step-down transformer? Well, the answer lies in these two formulas. This top one you might recognise as Ohm's law, which relates the voltage, the current and the resistance, and we've used that lots of times in that kind of formula triangle. This second one down here is all about the power of a system. Power is measured in watts, and we've got some other videos that talk about this. And the power is equal to the volts times the amps. It's V times I, the voltage times the current. Okay, now we can actually combine those two. So a little bit of algebra for you here. I'd like you to write another formula, please, that starts off P equals, but instead of writing the V, I'd like you to write what V is equal to. V is equal to I times R. So you just write out this formula, but instead of writing V, put I times R and see what happens. Okay, you can do that now, please. Right, here we go. Instead of V, I'm going to write I times R, so that's my V, and then we've got another times I on the end as well. And we can write that more shortly as I squared R. Again, you may have seen that. Power equals I squared R is quite a common one in there. Now, something to note here. I squared, the current squared. So power in this particular case is quite dependent upon the current, and it's the current that's the bad thing when you're transporting electricity. When you put electricity through a wire, the wire gets hot, and we've all seen this on things like electric heaters or hair dryers. If you look inside them, you can often see a curl of wire, and sometimes that curl of wire will start getting glowing red hot, especially if it's been dropped or something like that. They shouldn't get red, but sometimes they do. And that's because the electricity going through the wire makes the wire get hot, which is what you want in a heater. It's not what you want in these wires, because when you're pushing a certain amount of energy in here, you want to get the vast majority of that energy out the other end. You don't want it wasted in between. And when you put amps through wire, that's what makes it get hot. And that hot, the heat will be lost to the air. So it's being inefficient. Energy is neither created nor destroyed. All the energy you put in will go somewhere. Some of it will be lost as heat, and the rest will get into your house. And obviously you want most of that. So we don't want to be wasting it as heat. And because of this I squared, what that means is that if you 10 times the current, you 100 times the power. See, the power's got an I squared in there. So if you 10 times the current, you will 100 times the power, which means you 100 times your loss in heat. Bad idea. So, for this reason, we want to keep the amps low. We want to keep it at a low current, but if we have a low current, there we go, low current, we need a high voltage so that we get a decent amount of power through. Yes, you following me there? This means we need to have a low current so that we don't lose lots of heat. But if we've got to have a low current, we have to have a high voltage. Hence the getting on for 500,000 volts in these ones here. Okay, I hope that's made that a bit clearer to why we do that there. By the way, these transformers here, hideously dangerous. So if you ever see them at the side of the road, you sometimes see they've got little fences around them there. There's usually warnings saying, don't touch this stuff. It's there for a reason. Don't muck about with them. The casing's obviously very safe. It's all been insulated and things, but don't ever muck about with them. And really, don't even think about climbing pylons. Every now and then, there's some idiot who does that. Oh, they've got a kite stuck up there. They go down and try and rescue it, and they end up fried in hospital. So, you know, really, don't mess with electricity. It's dangerous. But, of course, you're all sensible people. So we're going to have some fun with more electricity, and I'll see you later, Batty fans.
Mwahaha! Mwahaha! Mwahaha!